We're going to visit our data on the number of egg yolks and the amount of cholesterol in different cake recipes in a little bit more detail. So you see some review of the scatter plot we had before, and in your notes, take just a second and draw a line that you think kind of best summarizes that trend between our two quantitative variables. All right, hopefully you're drawing something kind of along these lines. Everybody's is going to look a little bit different, and I just want to remind you of some notation that maybe you've seen before. So from algebra class, if you remember just one equation, you probably remember that y equals mx plus b equation for a line. And in this equation, remember m was the slope of the line. So that rate of change here as x goes up, what happens to y? And then b was that y-intercept, where this line crosses the y-axis. We're going to use a similar formula in stats, and it's actually the exact same formula, but we just use slightly different notation. We're going to use y hat to denote the predicted y, and instead of b for the slope, we're going to use for the intercept, A is going to be our y-intercept plus bx. And in this case, b is our slope. So in case it's been a little while, just a reminder, the slope always goes with x. So b is our slope in this. And if you have a highlighter handy, make sure you highlight this formula and are really comfortable with it. So this is just the formula for our line that we drew above here. So this line that best summarizes our data. So we have a bit of a question here. How do we define this best line? What line is better than all the others? Your line may be similar to this, but maybe not exactly the same. So what might make one person's line better than another? Think on that for just a minute. So there's actually several criteria, different criteria. The criteria we're going to look at is called the least squares regression line. So by that, we first need to understand what we mean by residual. So this point, let's use this one for an example, is y, my observed y value, somewhere here at 100-ish, a little over 100. I want to see what is that error in prediction. How far off does my predicted line miss that point? So up here, vertically, from that point right up to the line, this is y hat, the predicted value. So that difference between what I observe, the y value that is the actual data point, I'll label that here, and what my line predicts will denote that y hat, that's this guy up here, this is what my line is predicting. That difference is called the error or the residual. I'm going to so here's kind of our mathy version of that formula. I'm going to put this in plain English too. So our residual is that error in prediction. It's the observed y minus the predicted y. So this discrepancy. And ideally, we want these errors to be as small as possible anywhere we go on this line. Overall, we want that discrepancy or error to be as small as possible. So that's this line that we're defining as our best line, is this least squares regression line. And it is the one that has the smallest squared residuals. And I'll just write that reminder here, help get it stuck in our head. E is our error or residual, is the actual y from the data set, and y hat is what our line is predicting. We want this to be as small as possible across all the points. Just a quick observation, it says they're squared, and it's squared for a reason. If we take this point, for example, and we think about the residual, my observed y is up here around 200. The predicted y is down here around 100. So 200 minus 100 will give me a positive value. So this guy would have a positive error or positive residual. If I calculated the error for this guy, my observed value, this y, is smaller, so I'm going to do smaller minus bigger. This residual would give me a negative value. So the points above the line have positive residuals, points below the line have negative residuals. So that's why we square them in the definition below, because we don't want these to cancel out to 0. We want just that overall magnitude of the differences. All right. So most important thing to know right now, this definition of residual or error, and then also that equation of the line in general for stats. All right, so question is, now we know we want the best line is the one that has this overall smallest error or distances of points to the line. And this is our general form, so we need to figure out with that criteria, giving us smallest distances of points to the line, how can we find the formulas for the intercept and the slope that give us that best line? If you've had calculus, then that's how we're going to do it, but I'm not going to go into that in this course. So here, first, notice our slope. If we do some calculus, take the derivative, set it equal to 0, and so on, you're going to get that the slope is found by correlation times standard deviation of the y's over standard deviation of the x's, and the intercept, A, is given by mean of the y's minus B, that was our slope we calculated, times mean of the x's. So just a heads up, make sure you always calculate slope first, this B, because you need it to find the intercept. So one last thing, some of this notation we haven't used before, y bar, sy, sx, we have used s and x bar, so this should be kind of intuitive, but just to point it out, here where we have our variables, if you guys have the data in a chart, I would definitely recommend labeling. So remember, x was the egg yolks, and we're using that to predict our response, y, the cholesterol. X is not always going to be on the first row. So read the problem, see what you're trying to predict. That's y, and then x is what's influencing that. And then over here, mean, we know the mean of the data is x bar for my x variable. Since I've got a y variable, the mean of the y variable is y bar. And then standard deviation is normally s, so we'll use subscript x to say standard deviation of the x variable, that's the 2.17, and sy is the standard deviation of our y variable. Now that we have some ideas down, in the next video, we'll actually look at working out one of these problems.